Okay, everybody, welcome to the Motivic Geometry seminar. It's really a pleasure for me to introduce today's speaker, Ieke Moerdijk from Utrecht University. We'll talk about the profinite completions of Quillen model categories. Please, Ieke.
Yes, Paul, thank you very much for inviting me to give this talk in a, for me, somewhat awkward and unusual way. We were chatting a little bit before I started about and reminisce about the time that Arne was in Utrecht. But I also mentioned I don't really see who's in the audience, so it would be nice if some people turn on the cameras. If not, anyway, I will do a share screen very soon, so I won't see very much of you anymore. Johan has left his sailboat. Okay, so I will go through some notes that I prepared for this talk, and the notes are based on the paper that I wrote with Thomas Blom, also known as Thomas Blom, and we have a preprint on the archive where you can read all the details. There's some more people I know showing up. So hello. So I will now start to share screen and probably lose the image of many of you. Let me reorganize my desktop a little bit. Okay, so here's a theorem, and I would like to take you through the theorem and a list of examples. So the theorem is about a simplicial model category, which has the property that all objects are cofibrant. I will say something more about this condition as the talk progresses. And the theorem is somewhat vaguely stated at the moment. So if you wonder about some specifics, I hope it will become more clear as we go along. So I fix a small full subcategory C, and I assume it's closed on the finite limits. Now, E is a simplicial model category, so in particular it has tensors and cotensors, and I will also assume that this small category C is closed under cotensors with finite simplicial sets. So that's the second bullet there. Of course, since C is also closed on the finite limits, it's enough to assume it's closed under the standard simplices, cotensoring with the standard simplices. And then I can consider the category pro of C. So that's the pro completion of C. So if you don't quite remember what it is, I will remind you on the next page, I believe. And I claim that there will be a model structure on pro C, and it admits a left Quillen functor from the model structure that you started with, E. So if you think of C as some small objects in E, finite-like objects, then pro C is some sort of completion, pro completion of E, where the finite objects are those of C. And the model structure, here's some remarks about the model structure. So first of all, it will again have the property that all objects are cofibrant. And secondly, there will be a specific and explicit description of weak equivalences. Namely, you should fix some class of objects, set of objects, because C is small, T in C, T for test objects, and assume these are again closed on the cotensors with finite simplicial sets. And then you test the weak equivalences by mapping into these test objects. So let's stare at this a little longer. So X and Y here are maps in Pro C, and so Pro objects, formal inverse limits of C, and you can form this object map XT by using the fact that the cotensors of T are again in T. So you this naturally has a simplicial structure. Okay, it will become a little bit more clear on the next page, I hope. So the theorem is not very well formulated. I'm well aware of that, because T does not occur in the formulation of the theorem. So the weak equivalences depend on a choice of T. So in fact, there are many model structures you can construct in this way, and they're related by Boutsworth localizations generally. So let's see what I say next. Oh yeah, the other important thing is that all these model structures will be fibrantly generated. So if you already know some examples of model structures on Pro categories, you will be aware that this is not an exception. They're fibrantly generated. Now, I don't know how it is for you, but I'm much more used to co-fibrantly generated model categories with which I more or less grew up. And the same is perhaps true for my collaborator, Thomas. So it's sometimes a bit tricky to work with these fibrantly generated model categories. Okay, so here is the remark about T that I already made. So let's go over the theorem once more before we go to the next page. So I start with the simplicial model category E. I select some objects of which I want to take the Pro completion. And then there will be some conditions and structure under which I can equip the Pro completion of C with a model structure, which is related to that of E. So the next page, I think, is just a reminder. That's the next sentence before the examples, recap on Pro. That's the next page. Okay, so Pro C is the free completion of C under filtered inverse limits. Okay, and so its objects are diagrams with values in C, and the diagrams are indexed by an arbitrary small category, which I call I here, and I has to be filtered. I take my diagrams to be covariant, as I indicated here, and so here's a reminder of what I mean by, or what is meant by filtered, also because there is always the possible confusion with contravariant and covariant and so on. So a filtered category has to be, the three conditions are there in the pictures. The filtered category has to be non-empty. For any two objects, there is a sort of smaller object mapping into these two. And for any two parallel arrows, there is some arrow equalizing these given parallel arrows. Okay, now the morphisms, there's a formula for the morphisms. So there are two homes here. The first home is the home in Pro of C, and the second home on the right-hand side of the line is the one in C, the given category C. So if you want to define home XY, Y is formally in inverse limits. So if y is indexed by little j's, then for every j, you should have a map into the inverse limit. So that explains the first lim j. And then the only way to get a map from x to yj, if you know nothing about x except it being a formal inverse limit, is first to project down to some I and then map to yj. So that explains the formula that you have for the morphisms. So a morphism gives for every j an equivalence class of maps from the various xi to j to yj. Okay, now C is of course included in Pro of C because you can take for I the point. So it's a constant diagram. And under this inclusion, a diagram indeed becomes the inverse limit of its values. So that sort of explains that Pro of C is the completion of C under filtered inverse limits. And it has a universal property, which I didn't state. Okay, there's another, these are very classical things. There's another way of constructing C when C has finite limits. Namely, you take the left exact functors from C to sets, and you take the opposite of that category. The description is related to if you want to understand that description, maybe it's easier to go to the dual case. The incompletion of C is the free completion under filtered co-limits. And you know that the free completion under all small co-limits is just the pre-sheaf category. So if you play around with that, it's just a matter of relating these left exact co-pre-sheaf, so to speak, to the fact that they're indexed by that they have filtered inverse limits of representables. Or I can say it more clearly in the pre-sheaf case. So a pre-sheaf on C is a filtered co-limit of representables if and only if it sends co-limits in the index category to limits in sets. So that's the dual case where C has finite co-limits. So that explains this formula, or maybe it doesn't quite explain it, but it's easy to figure out for yourself on the basis of what I just said. So that's a very handy formula from which you can easily conclude that Pro of C has all limits and co-limits, for example. Okay, here's the way this this equality is related. It's also more or less contained in what I just said. So C is contained in Pro of C as the constant diagrams, and it's contained in these left exact co-pre-sheaves by the Yoneda embedding. You have to think a little bit about the ops here, but you see that the representable given by maps out of a little object C, of course, preserves limits, so it's left exact, and it's contravariant in C, so that works out fine. And that equality here is, of course, meant to be an equivalence of categories, or rather a canonical equivalence of categories. Canonical by the universal properties of the categories involved. Okay, now you probably know, even if you haven't studied too much of the pro and ind formalities, which go back to SGA, for example. There's a long explanation in SGA of these things. I'm sure you know many examples. If you start with finite sets and you take its pro completion, that's the category of pro finite sets, and it's the same as the category of stone spaces. There is a category of pro finite groups, which we all learn about when we study the fundamental group of a scheme. And another context familiar to you, to many of you, will be the occurrence of pro categories in homotopy theory, in particular Artin Mazer et al. Homotopy theory. So here is a quick reminder of the definition. if you take a topos, you can look at the hypercovers of the topos. Now, the easiest way to think of a hypercover is it's some simplicial object in E, and if you put yourself in E, imagine that you live in E, it should look like a contractible count complex. So contractible count complex has filling conditions, and these filling conditions should then hold locally in E. Now, if E is also locally connected, there will be a good pi0 functor from E to sets. So if you have a hypercover, you can take its pi0 at each simplicial level, and this will give you simplicial set. And if you do that for all the hypercovers, you will get a system of simplicial sets. And then you have to notice that these hypercovers, two hypercovers can be refined, but this refinement is only really well defined or even unique up to homotopy. So you get something in pro of ho of simplicial sets. The pro category of the homotopy category of simplicial sets. Okay, that's just meant as an example. Okay, so now I will go back to the theorem. Maybe let's start it again for a minute. So I have a simplicial model category. I have a small category C, of which I take the pro completion, and I produce a model structure on it by providing you with a subcategory of C, of which I'm thinking as the test objects to test the weak equivalencies. That's that line here. Okay. So now let's go to the examples. So I think much of the talk will be concentrated on these examples because I think we had, I will come to that, but our motivation for the work was actually twofold. First of all, we wanted to sort of have a unified and simple treatment of many of these model structures that occur in the literature. And secondly, we wanted to, and that was the original motivation, to study profinite operads, or the homotopy theory of profinite operads, or even profinite infinity-operads. Because if you take the profinite completion of an operad, simplicial operad, you don't get an operad on the nose because this profinite completion doesn't preserve products. So there's a slight problem there. So I will come to this motivation when we go through the examples. Okay, now maybe historically one of the first examples is the following. You take the model category of simplicial sets, category of simplicial sets, with the classical Quillen model structure. That's the KQ here, and then you localize it for mod P cohomology. So it's about left-Bouswirth localization of the classical Quillen model structure. And then I have to choose my category C, and I take for C the category of what we call lean simplicial sets. And a lean simplicial set is a simplicial set which is degree-wise finite and is n co-skeletal for some n. So I will just call that co-skeletal. And therefore, this subcategory T has to consist of fibrant objects. I hope I wrote that, but I don't want to go back to the first page. So T is the category of lean count complexes. And then you get a model category of a structure on pro of L, but pro of L turns out to be the category of simplicial profinite sets or simplicial stone spaces. And in this way, you recover the model structure of Fabien Morel. Okay. So there's another way to do that. You could also just work with the Quillen models ambient model structure, and then take for T the local objects, the P local objects. So there's a sort of a commutation of left bounds with localizing E and shrinking the category T, to which we will perhaps also come back depending on the time. But there's a lot of variation in this formalism. So in a way, a simpler one, but historically later example is you take again just the category of simplicial sets with a Quillen model structure. And for C, you take again this category of lean simplicial sets. So I repeat, degree-wise finite and co-skeletal. And for T, you take the lean complexes, and you get a model structure, all of whose objects are cofibrant again, as I mentioned in the formulation of the theorem, and with the weak occurrences detected by this T, and it's exactly the quick model structure. Is quick here?
Arion, are you here? Don't think
Arion,
so.
are you here?
Don't think so.
No. Okay. I only see a few of you. Okay. So these are two classical examples. I'm sure familiar to some of you. And now some more modern examples, shall we say. I can play exactly the same game with the Joyal model structure on simplicial sets. And then I take for L, again, my lean simplicial sets. I take the lean simplicial sets so that, and it's still here on the sheet, so that pro of L is the category of simplicial profinite sets, or simplicial stone spaces. And for T, now I have to specify a category of fibrant objects, and I take the lean infinity categories. So what you get is what might be called a model structure for profinite infinity categories. So it's a model structure on simplicial stone spaces. Now, Thomas and I have tried without much success to relate this to some form of categories enriched in profinite sets, profinite simplicial sets. So classically there is the equivalence between simplicial categories and the Royal model structure and complete Segal spaces, and we were unable to relate this to something that looks like profinite categories. But it is possible to have a complete Segal version of this, and it goes as follows. So the definition is a bit more complicated. Let's stare at it a little bit longer. So I consider the category of bisimplicial sets. So that's example 4 here, with a resp model structure. And what's this resp model structure? It's explained here in these clauses A, B, C. So a bisimplicial set is a simplicial object in simplicial set, so it can be equipped with a ready model structure, ready with respect to delta, and Quillen with respect to simplicial sets. And then you localize it by 2 sets of maps. And I didn't write localizing maps here, but I wrote the conditions for the map for objects to be local. So an object is local for the so-called Segal condition if so this is an object, it's a simplicial space, a bisimplicial set. If the map from xn to x to 0i times x to in over xi is a weak equivalence for each n and I. And so these maps are the restriction, this map from xn to x0i is the restriction, the face map to the first I+1 vertices, that's along this map, and the other is to the last n minus I vertices, and they overlap in just one point, which is the ith vertex. So that's a Segal condition. And then there is a further so-called resp completeness condition. You take the simplicial, you take the internal home x to the j, that's an exponential, and which you can evaluate at the endpoint. It gives you a map to x, and that should also be weak equivalence. And j here is the nerve on the discrete category of two objects, which you view as a discrete simplicial space. Okay, now you can form the category of bisimplicial stone spaces or the category of simplicial objects in simplicial stone spaces by this sort of lean trick, but now it has to be lean in two directions. So for C, I take the what I call doubly lean objects. So they have to be co-skeletal in both simplicial variables and degree-wise finite. And for T, I take the appropriate category of fibrant objects. So these are the complete Segal spaces in the sense of resp, which in addition are doubly lean, of course, because T has to lie inside C. So this gives you a model category of profinite complete Segal spaces. That's just the name, and you can prove more or less analogously to the more classical equivalence between quasar categories and complete Segal spaces. You can prove that this model category is Quillen equivalent to this one here. So profinite infinity categories and profinite complete Segal spaces are Quillen equivalent. Okay. Now I have a somewhat speculative example, but I wrote it down because perhaps one of you has some suggestions for a solution. So I start with a coherent site, and I assume that this the underlying category of this site is finite home sets. And then I look at simplicial presheaves on this site, and it carries many model structures, projective, injective, and possibly several in between as basic model structures, which can then be localized. And so the canonical localization is related to the Grothendieck topology by just, well, one way to formulate it is that you test the weak equivalences just by taking the stalks, or taking this will be a site with enough points. So you test at every point you get the stalk is just a simplicial set, and you test the weak equivalences at that level. There are many alternatives to this. There's a Royal model structure on sheaves. There is the version by Jardine starting from a projective model structure, which is subsequently localized, and they're all Quillen equivalent. But I said in the beginning I would like to have a model structure where all objects are cofibrant. So that's why I took the injected version. Now, there is also a notion of lean here, because you can say when the simplicial presheaf is sort of doubly lean, it should be lean in the sense of the simplicial sets that occur as values of the presheaf, and it should be right-Kan induced from a finite subcategory S primed in S. So because the site is coherent, all the covers will also eventually occur in these finite subcategories. And then you can form Pro of LS, and Pro of LS will be equivalent as a category to presheaves with values in profinite simplicial sets. Now, I did not elaborate this example because I'm not quite sure what to take as my test objects, because I don't know how many fibrant objects there are which are also lean. Now, this is a problem that I haven't thought much about yet, but the problem occurred already in our first example, our motivating example, which is the next one on the list. So some of you will know that I've been rather preoccupied with the category of dendroidal sets lately. So here's a quick review of dendroidal sets. There is a category omega of trees. The trees look like this. They have a root, and they could have vertices with 0 inputs, or open edges, which are called leaves. And any such tree generates a colored operad where the colors are the edges and the operations are just generated by the vertices. So here's a binary operation from these two colors to this color. Here's a ternary operation, and here is a constant of this color. So these give you operad maps from such a tree gives you a freely generated operad, which I call omega of T. Omega S is the free colored operad on S. There are other ways to describe the morphisms, which are a bit like describing the morphisms in delta by phases and degeneracies. Exactly the same works here, but there are also isomorphisms in the category. So the category delta is completely rigid, but a tree can have lots of automorphisms. So because of this, there is a notion of normality for the presheaves, and a presheave, just a set value presheave or a simplicial set value presheave on omega is called normal if when you take the value x of t at some tree, it should have a free action of aught of t. So conditions like this are of course familiar from, for example, model structures on simplicial sets with a fixed group action. So it should not come as a surprise to you. And these dendroidal sets then carry a model structure where the fibrant objects are the infinity-operads. And the interest of this model structure lies in the fact that it is Quillen equivalent to simplicial operads. So it's some sort of combinatorial way of dealing with simplicial or topological operads. Now, you can do the following. You can look at lean dendroidal sets. They're again degree-wise finite and co-skeletal. I will come back to this notion of lean and explain it a little better to you a bit later. And you take for T the fibrant objects in this model structure, which are also lean. So those are the lean infinity-operads. And then you get a model structure on dendroidal profinite sets. And it's a model structure it's one way of defining what a profinite infinity-operad could be. So I want to make two remarks about this example and maybe also about the next. So first of all, this model structure does not have the property that every object is cofibrant, as I said, but our method, which I stated in the very beginning, this sort of generic theorem in the beginning, can be adapted to this case, be it with some effort. So I will not go into the details of that here, but there are ways out if you don't quite have that all objects are cofibrant. So maybe this also helps in the previous example about schemes. And the other remark I want to make about this example, I said somewhere that this was the original motivation of Thomas Blom and myself. We wanted to have a proper homotopy theory of profinite-operads because homotopy endomorphisms of profinite-operads are related to the Grothendieck-Teichmuller group, and this is known. There's several papers about this by Boavida and Morel, for example, and we wanted to have a true model category underlying this notion of homotopy endomorphism, which was introduced there in a somewhat more ad hoc way. So that was our motivation. So for these dendroidal sets, I worked out a while ago with Szynski that there is also a complete Segal version in style of resp, and this works also in the Profinite case. So I didn't spell it out here, but it's really analogous to what I just said about the simplicial case. So let's go back to that for a minute. So you have simplicial sets with a Joyal model structure, and bisimplicial sets with a resp model structure. They're Quillen equivalent, and they have Quillen equivalent sort of profinite completions. And the same is true for in the dendroidal case. You have dendroidal sets and dendroidal spaces, and they are Quillen equivalent, and they have both have profinite versions, which are again Quillen equivalent. Okay. So that ends my list of examples. So now a little bit about this business of lean, which was observed by maybe not the terminology. Thomas and I introduced the terminology, but the method was observed by several other people. Certainly not due to us. So you could ask, what happens to a functor category of a pro category? So if you have a pro category C, pro of C, and you assume that C has finite limits, then taking functors into this pro category will produce another pro category, pro of the functor category, provided A is finite. It's probably the next line. Yes. That's an old result of a PhD student of Joyal from the maybe late 70s or early 80s. Maybe Thomas has the, well, I have the year here because I have the reference here. Let's look at this for a minute. Yeah, there is a publication 1980, so the thesis is probably a little before, late 70s. Okay. Now, what do you do if A is not finite? Well, you can still do something if A has finite Holm sets. It goes as follows. The functor category of a pro category is again a pro category, but it's no longer true that pro of C to the A is pro of C to the A, but it's pro of a smaller category, co-skeletal functors from A to C. So co-skeletal of C to the A is a full subcategory of co-skeletal functors from A to C. And what do I mean by that? Well, if you have a functor from A to C, here's the diagram, here's the definition. If you have a functor from A to C, you can restrict it to some finite subcategory A primed in A. Let's take a full subcategory. You can restrict it, and then right can extend it. So that gives you I lowest, what I denote by I lower star, I upper star of F. And F maps into I lower star, I upper star of F. And if this map is an isomorphism, I call F co-skeletal. So it's good to notice here, since C has only finite limits, it's good to notice here that this right Ken extension, if you just write out the formula, it only turns out to involve finite inverse limits. Okay, so here's the formula. You have to have something which is covariant in this object A of A, and the inverse limit changes the variance, so you have to put as index thing set. That's at least the way I remember it. Something which is contravariant in little a, and then you take all the maps into the b's in this smaller category A prime. So that's a finite stuff here. Okay. So the example that we have used several times is if you take for A the category delta, the opposite category of delta, and you take for A primed all the objects of delta less than or equal to a certain number n, you get exactly the n co-skeletal simplicial objects in the usual sense. Okay, so then this formula here, pro of the lean simplicial sets is simplicial objects in profinite sets is exactly a special instance of this formula here. Okay, so that's the way if you take pre-sheaves or to deal with pre-sheaves with values in the pro category and write them as themselves as a pro category. So I would like to say a few things about the proof. And maybe the first thing to say is that we don't prove the theorem in the way I stated it, because the arguments become much more standard if you work in dual case. And it really becomes a usual way of constructing cofibrantly generated model categories. And I want to emphasize that maybe the interest of the paper, well, I said it in the beginning, the interest of the paper is maybe first to provide a unified treatment of many of these examples, and secondly to give a sense to what a profinite infinity-operad could be. But the interest certainly does not lie in the proof, in the sense that it's actually quite easy once you know what you're doing. But that's the case for many proofs, I suppose. Okay, so I turned everything upside down. I'm now looking at the category C with finite co-limits and finite tensors. So C sits inside the simplicial category, so C should itself be a simplicial category, and or at least, yes, simplicial category, and has finite tensors. And I form the incompletion of C. So I told you already that's contained in the pre-sheaves on C, and it's those pre-sheaves that send the co-limits, finite co-limits in C to finite limits in sets. And our original C on the first page was sitting inside a model category. So with the property that all objects are cofibrant. So now, since I've turned things upside down, there will be an ambient model category E-op, the opposite of E, which now has a property that all objects are fibrant. Okay, and now I will produce a cofibrantly generated model category in end of C. Now, we do that by taking some structure on C, which we derive from E. But you can do all this without the ambient model category E, or E-op in this case, and so that's what I meant by the sentence, axiomatize the ambient model category away. So we cooked up the notion of a cofibrant test category. So here's the definition. I don't think I will be able to get it on the page. Maybe just about. So what's a cofibrant test category? So you should think of this, I repeat, as a C sitting in a model category, simplicial model category, all of whose objects are fibrant, to see where these properties come from. So C is a small category. It has finite limits. It has finite tensors. That should be, sorry, what am I doing here? I forgot to dualize. I'm sorry. So it's what is written here is correct. Finite colimits, finite tensors. So this should be colimits and tensors, and it should be simplicial. And then there should be a subcategory, full subcategory of test objects. So you should think of these test objects as the cofibrant objects in C. And inside T, I specify two classes of maps, the cofibrations and the trivial cofibrations, which canonically I could just take from the ambient model category. Okay, and then I should have the following axioms, which will be true if indeed I take them from some ambient model category if it exists. So first of all, the initial object is a test object, and every test object is cofibrant. Secondly, these test objects should satisfy the push-out product property. So I spelled it out here. If you have a map in T and an inclusion of finite simplicial sets, and you know that this map is a cofibration, then the push-out product map is again a cofibration. So if you see this type of map for the first time, so you have a small object and a big object, and a small object and a big object. You tensor the two big objects to get the biggest object, and inside you can do the small object with the big object and the big object with the small object, and take the push out over the intersection. You get another map for the moment, and we ask this map to be a cofibration and a trivial cofibration. If either the map from S to T is a trivial cofibration as specified axiomatically, or M to N is a trivial is an anodyne extension of finite simplicial sets. Okay, now it would be nice if these trivial cofibrations are related to the weak equivalences as I want to define them. So we put that in as an axiom. It's maybe not absolutely necessary, but it's a more natural setup. So we say S to T is a trivial cofibration if and only if for any R, any test object R, if you map out of R, you get a weak equivalence of simplicial sets. And this notion of map here is just because T is closed on the tensors, you can tensor R with simplices, and this will give you a natural simplicial enrichment here. So an n-simplex in map RS, to be more explicit, is just a morphism from delta n tensor R to S. Okay, and then we ask this notion of, for this notion of weak equivalence, you can define this notion of weak equivalence also if S and T are not necessarily test objects, but come from the larger category C. So this gives you a notion of weak equivalence between maps in C, and we ask that the push out of a trivial cofibration between test objects will still be a weak equivalence in C in this sense. And then I said that E-op has the property that all objects are fibrant, and that's reflected in this final axiom. Any C has the right lifting property with respect to these trivial cofibrations among test objects. So if you have a setting like this, and you take the int completion of C, it's quite standard to construct a model structure on int C. I don't know whether it's on the next page. Yes. Standard argument gives a model structure on int C with weak equivalences detected by map T blank. So this map so a map from X to Y is equivalent if and only if the map from the morphism from map Tx to map Ty is a weak equivalence for all T. And it's easy to write the formula for map Tx if X is an int object. It's just the co-limit of all the morphisms map T and then the objects constituting the formal co-limit. In other words, for this notion of map, the object T remains compact in the int completion. Okay. Now, the variations which also occur in the examples, or by which you can lengthen the list of examples considerably, is you could just shrink T, and then you get more weak equivalences, but this gives you a right Bousford localization. So that's maybe a little bit, you have to think a little bit about this, because we work with left now in the dual case with cofibrantly generated model categories, but we produce right Bousford localizations. But this fits in well with the motivating examples in the beginning on these pro categories where we have familiar left Bousford localizations, like Morel being a left Bousford localization of Quique, if I may express it this way. Okay. So this Quillen pair also occurs naturally. So remember, I have opt the E, so I use a different letter now, F. And just the universal property of the int completion will give you a map, plus the inclusion from C to F will give you a map from int C to F shriek, which will produce filtered co-limits by definition of int, by the universal property of int. But it will also produce finite co-limits, because this inclusion does, we assume that C is closed on the finite co-limits. So and this function will have a right adjoint, and it's immediate from the setup that this is a Quillen pair. So this is exactly the dual of this pro completion model category that I stated in the very beginning. I can look at it again. Yeah, it's here. So this one here, from E to pro C. So this is now the left Quillen functor goes out of the ambient model category. Whereas here, it goes out of the right functor goes out of the ambient model category. So, although this was not among our original purposes, of course, we wondered whether there are some interesting examples to be found in this dual int case as well, and this will be my last remark. So this is analogous to somewhat analogous to what some other people have done, like Barnea typically. You could get combinatorial versions of more familiar cofibrantly generated model categories by playing this game. So I mentioned two examples here. So you could take the category of compact Hausdorff metric spaces, or some small category that possesses finite co-limits and has cotensors by superficial sets. and I take as my test objects realizations of finite simplicial sets. They're of course inside this category C. And you get a model structure on in C. Now there isn't an ambient model category immediately because these are not, well, I don't know what to say, but anyway, it is still Quillen equivalent to topological spaces because it can be directly related by zigzag of Quillen pairs from simplicial sets. And then topological spaces with structure can be modified in the same way. I just left it at this single sentence, I think. So if you have algebras for a topological operad, you could take for C, or for T rather, a free P algebra generated by such a small compact space, and play the same game and get a combinatorial model category, which is Quillen equivalent to the category of P algebras with the standard model structure. So that's it. Thank you for your attention. So let me put up the first theorem again.
Thanks for a wonderful talk, Ieke. Now everybody in the audience can unmute themselves and we can give Ieke a well-deserved round of applause. Ready, set, go. Okay, great. Then I can start with the first question, and then the audience can start asking their questions afterwards. So can you comment more on the connection with pro-infinity categories?
Yes, there's also something in the paper about this. So you could take the homotopy coherent nerve of this category C. That gives you an infinity category using the simplicial structure of C, and take the infinity pro-completion of that, and you will get something which is equivalent to the infinity category associated to this model category. So there's a very precise statement to be made there, but it's worked out in the preprint.
Okay. Okay, I'll take a look. Thanks. Then,
at the very end, I think we call it an appendix.
Okay. 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 Let's see. There's a. Ieke, can you see the question in the chat?
Well, my Zoom window is very small now, so.
Okay, then I can read it for you. Let's see. So the question states: does profinite completion of model categories commute with Basler localizations?
Yes, in a sense. So what happens in the examples? I don't know whether it's possible to make a more general statement, but if you localize this this base for the profinite completion C by shrinking the class of test objects, now you get more weak equivalences. That corresponds to exactly to a Bousfield localization of the ambient model category. And in fact, I mumbled something like this, but perhaps not very clearly, about Morel. You could get the Morel structure in two ways. You could start with a Quillen model structure. If I'm not mistaken, you could start with a Quillen model structure on simplicial sets. Take lean simplicial sets, and as your test objects, the mod P local lean COM complexes. Or you could immediately start with the mod P localized Quillen model structure and profinitely complete that. I will give you the same result. So with a specification of what I mean by the left bounded localization of Pro of C, the answer is yes.
Mm-hmm. Okay, wonderful.
So I have a question. If you cut down E to the smallest simplicial model category generated by C, do you get a better improvement in the result?
If you cut down?
If you assume that C is sort of generates E as a simplicial model category, so the way that you do it, you can replace E by anything bigger,
Yes.
and your result would still be true.
Yes.
But you could also make E as small as possible, which would be the simplicial model category generated by C. And if you make it as small as possible, do you get a tighter result?
I don't know exactly how to answer that question. C has to be, yeah, I don't know exactly how to answer that question. I mean, you could probably say something about the Quillen pair, like the right Quillen functor will detect weak equivalences or something like this. You can probably state it in terms of better properties of the Quillen pair, but I haven't thought more about this. I cannot answer it on the spur of the moment. But that's where I would look how to answer it. Maybe Thomas has something better to say if he's still here.
Yeah, so my internet connection was down during the first half of the question. So
if C generates E in some sense,
yeah.
To what extent does Pro C get closer to E? I think that's a way to paraphrase. Chuck, is that the correct way of paraphrasing your question?
That's a fair way to say it, yes.
I wouldn't know. Yeah, no, I don't know how to answer that question either.
Okay, great question, Chuck. So there's
more to do. Good question.
Great. Anybody else? Please go ahead with questions. Oh yeah, David, please.
Yeah. So with these profinite infinity categories, I guess I'm sort of wondering, like, what are natural examples? For example, is the category of profinite spaces in one of the senses? Does that have a natural structure as a profinite infinity category in the sense that you gave?
Well, if you work with some sort of gross topos and on topological spaces, maybe you can get close to that. But for using this formalism, yeah. But we in some sense, what we did with these compact spaces is a sort of a jewel of that, but then completely analogous to what you described. But your construction is rather large.
Mm-hmm.
So you would have to maybe have a nice category of topological spaces so that you can put the finite co-limits inside the Grothendieck topology, and then try to play a bit with the sheaves to get close to what you want out of this formalism.
Mm-hmm. Yeah, and I guess I'm just wondering in general, do you have any examples in mind for describing a profinite, describing some sort of homotopy by viewing it as a profinite infinity category in the sense of, you know, doing this construction with the Joyal model structure?
No, we did. At least I didn't have any particular purpose with pro infinity categories in mind at all. As I said, our main purpose was to get a proper notion of what could be a profinite infinity-operad, because these play a role in this Grothendieck-Teichmüller business. Also, if you can work with model categories, it has a little bit more structure than the infinity categories, of course. So it's
right.
It's a bit more informative.
Good. Any other questions from the audience? Doesn't seem to be the case, so let me thank both the audience and Ieke for this wonderful talk.
My pleasure.